South Atlantic storms batter the scientific research vessel, the James Clark Ross, as it heads to one of the remotest spots on the globe. On board, a team of scientists from the British Antarctic Survey, intent on conducting the most comprehensive study ever of a little-known group of volcanic islands. Their motive? To try to understand a phenomenon that they have dubbed the Earth's crust factory. The team's destination? The South Sandwich Islands, a chain of volcanoes situated 2,000 kilometres southeast of the Falklands. These remote islands were first discovered by Captain James Cook on HMS Resolution in 1775. Since then, visits have been infrequent. The absence of natural harbours and dangerous mid-ocean swells ensured that they remained the province of local wildlife. But the significance of these islands lies not with their unspoilt character, but in their unique geological setting. The geoscientists on the expedition are here to study the Earth's crust. They call the project the Sandwich Lithospheric and Crustal Experiment, or SLICE for short. Marine geophysicist Rob Larter explains.
The South Sandwich Islands exist because they are in an area of intense geological activity. A slab of ocean floor is sinking into the mantle to the east of the islands, and the immense forces involved in this process are responsible for moving the tectonic plate on which the islands sit at a rate which is about 3 times that of any of the surrounding tectonic plates.
The South Sandwich Islands are in fact the tops of 7 submerged volcanoes. These volcanoes stand on a relatively small D-shaped tectonic plate, one of the many which make up the surface of the Earth. The Sandwich Plate is bounded on one side by an oceanic ridge or spreading point. Here, magma from beneath the Earth's surface rises up through the ocean floor, forming new oceanic crust to fill the gap left by the gradual movement of the plate eastwards. The source of the plate's movement is found on its eastern boundary, which overrides part of the South American tectonic plate. Where the two plates meet, the older South American plate sinks beneath the Sandwich Plate in a process known as subduction. The weight of the sinking plate drags the Sandwich Plate away from the mid-ocean ridge. As the South American oceanic crust sinks deeper into the Earth, it becomes hotter and releases water held within it. This causes the overlying mantle rock to melt, and because it becomes lighter, it rises and forces its way up through the surface of the Sandwich Plate to form volcanoes. These volcanoes are the beginnings of new continental crust. For the scientists, the islands and the ocean which surround them offer one of the most explicit demonstrations available anywhere on the globe of how the Earth was formed. Because of the range of complex phenomena at work, the SLICE project was conceived as a 2-phase operation. One team of scientists remained aboard the James Clark Ross to conduct a detailed seismic survey of the ocean floor. A second team transferred to the Royal Navy Ice Patrol vessel, HMS Endurance, which would tour the island group, dropping off field parties by helicopter. These field parties would collect geological samples and record a whole range of data about the physical structure of the islands. On board the James Clark Ross, scientists began preparing the equipment for their seismic survey and for their measurements of the Earth's gravitational and magnetic fields. The combined results of this data would enable them to produce detailed pictures of the ocean floor and to estimate the age and composition of the rock beneath the surface. The scientists' first task was to deploy 28 ocean-bottom seismometers. These devices rest on the sea floor and detect seismic signals produced by air guns on the ship as it moves over them. The same seismic signals would also be recorded by scientists on the islands. Geophysicist Ed King.
As the ship steamed towards our particular islands, we had recorders running with a different kind of seismometer that was tuned to the sort of frequencies we could expect from the air guns. and as the ship steamed past the island and away in the opposite direction, we continued to record. So that will provide a valuable addition to the data recorded on the ocean bottom seismometers, and it all has to be integrated together.
Because the seismometers operate automatically, they have to be programmed to resurface at a specified time. As a result, the seismic survey had to be completed in good time to return and collect them. The team also dropped a series of floating sonobuoys to record the seismic energy reflected from the seabed. The equipment's short battery life meant that there was little time to complete the main survey. These devices, originally developed for submarine detection, send their data back to the ship by means of small VHF transmitters. While the team on the James Clark Ross continued with their preparatory work, field parties were deployed by HMS Endurance. Practically all the beaches in the islands are narrow, steeply shelving, and subject to at least a metre of ocean swell, making boat landings hazardous. The only safe way to deploy field parties was by helicopter, and this meant establishing a continuous ferry service of men and equipment to the islands. Because of their extreme remoteness, many of the islands had not been visited since the last geological survey in 1964. And for volcanologist John Smiley, the SLICE project offered a unique opportunity to study phenomena of fundamental importance.
The South Sandwich Islands are situated at a convergent plate margin. It's a place where two slabs of oceanic crust are in collision, and in the act of collision, one is being consumed beneath the other. As a result of this process, melting occurs in the mantle deep within the Earth, and these melts erupt to form volcanoes. And what we're seeing are the earliest stages of the transformation of that crust into continental crust. What we have is one of the world's best continental crust factories.
While the geological work progressed, the helicopter continued to bring other specialists to the islands. Although terrestrial biologist Pete Convey was not involved in the SLICE project, he was able to use the survey as an opportunity to visit the islands and conduct the first comprehensive biological survey of the group.
There are tens of thousands of penguins in most of the places that you land. One or two places there's over 1 million, and then there are seals as well, so it looks very rich, but technically they're part of the marine environment. There aren't many species, and they're very small, but if you look in the right place, there are quite a few of them. Most of the islands are 20 to 40 kilometres apart, and in the weather conditions you get typically around there, that is actually a very major barrier to colonisation. So if you start looking at the plant communities around specific fumaroles, or if you start looking at the animal communities on whole islands, there isn't a very strong link between the community on one and the community on the next.
On board the James Clark Ross, the seismic survey team made preparations to begin the survey. The survey technique was first developed in the 1940s for oil exploration. It works by generating artificial seismic waves, which are then recorded as they are reflected back by the ocean floor. The time which the energy takes to arrive back at source and the degree to which it is reflected or refracted by the rocks enables scientists to determine the structure of the underlying geology. For the SLICE survey, seismic signals would be generated using powerful air guns. These air guns would be towed behind the ship and generate seismic signals by releasing blasts of compressed air into the water. Reflections of the seismic energy from the seabed and boundaries between the types of rock beneath the seabed would then be detected by a string of sensors also towed behind the ship. Inside this 2.4-kilometre tube were 96 25-metre-long groups of highly sensitive microphones. They record 30 seconds of data from each shot of the air guns. In the sonar control room, preliminary results were printed out by computer.
Stop.
towed seismic array is designed to produce a profile of the ocean floor, the work had to be continuous. During the survey, the James Clark Ross would make a series of 4 600 to 900 kilometre runs across the South Sandwich Trench.
We set out to try and obtain some typical cross-sections across the trench and the island arc. And if we had, say, only collected one profile, we'd only made one run across the trench and the island arc, we would never know whether the features we observe on that profile were typical or unique to that profile. So 2 of the profiles are located as close as we could go to islands, and 2 of them go about halfway between islands.
At 8 kilometres, the South Sandwich Trench is the deepest part of the Atlantic Ocean, and the seismic profile which began to emerge provided the clearest picture yet of a phenomenon which the geologists described as rollback. The advancing Sandwich Plate appears to be pulled eastward by the subducting South American Plate, which is peeling backwards in a rolling motion. It is this rollback which geologists believe accounts for the unusual speed with which the plate is travelling eastwards.
In essence, it's sucking the overriding plate with it, and that provides an extra driving force for the plate that the arc is sitting on. And that's one of the reasons why such plates can move relatively fast.
In an effort to determine the precise rate at which the plate is moving, geophysicists in the field parties made a series of very accurate measurements of the locations of Candlemas and Thule Island using global position satellites. These measurements enabled them to establish positions on the island down to an accuracy of less than 6 millimetres.
Colleagues of ours had similar receivers set up in South America and in the Antarctic Peninsula, about 2,000 kilometres away. And all of the receivers were receiving signals from the same set of satellites at the same time. Those measurements were repeating to the level of about 6 millimetres. Imagine having a 2,000 kilometre long ruler and measuring that distance to within 6 millimetres. It's an amazing technology.
Scientists plan to return to the islands in 2 years' time to make a second series of measurements and accurately determine the distance the plate has moved. While the James Clark Ross made its seismic survey runs, back on Endurance, the process of landing field parties continued. The project could count on only 17 days of air support before the ice patrol vessel had to resume service elsewhere, and visiting all the islands in the 350-kilometre chain set an unrelenting pace. Bellinghausen Island is one of the smallest in the South Sandwich group, less than 2 kilometres long by little more than a kilometre in width. Although no volcanic eruptions have ever been documented here, the huge clouds of gas emitted from its vents indicate that it is still an active volcano. In this primeval landscape, the scientists were offered a rare glimpse into the history of our planet at an embryonic stage in the development of the Earth's landmass.
For me, it was a lifetime achievement to work in this region. I'm very glad I've done that. Speaking as a professional person, as a volcanologist, it's also doubly exciting to work on active volcanoes where you see the actual processes of land formation taking place in front of your eyes in many cases. But there are also other ways which I'm interested in volcanoes, and the way in which they impact their environment, particularly the atmosphere, also interests me. And volcanoes impact the atmosphere particularly by the gases they evolve.
Although volcanoes erupt for only 1 to 2% of their lifetime, they're constantly giving off gases into the atmosphere. So far, little research has been carried out into the precise nature of these gases. But the close proximity of the South Sandwich Islands to Antarctica makes them of particular importance in assessing any contribution they might make to the destruction of the Earth's ozone layer. One of John Smiley's experiments on the expedition was to collect gas samples from the volcanoes, using an instrument designed to capture and concentrate trace amounts of organic or carbon-based compounds in volcanic gases.
Certain organic compounds, CFCs, are potentially being given off by volcanoes. Now, the current thought is that these are entirely anthropogenic, so it struck me, why shouldn't we look for a natural source if there is this hint that potentially these things do exist? So part of my work was to capture some of these gases, bring them back to UK and analyse them for a range of organic compounds. At this stage, we don't know what organic compounds occur there because so little work has been carried out, but potentially if these compounds are present, then they have a major impact on our understanding of destruction of the ozone layer.
As the seismic survey progressed, the scientists were gathering increasingly detailed images of the South Sandwich Trench and the island arc. But to get a clearer understanding of the geological makeup of the plate, additional tests were required. 2 magnetometers, one towed behind the ship and the other on board, allowed the team to record the magnetic configuration of the ocean floor. By this means, they hoped to date the rock and determine some of its physical characteristics.
Magnetometer surveys over oceanic crust enable us to determine how long it was since it was formed at a spreading centre. It's possible to do this because when molten rock cools, any magnetic crystals in it align themselves with the Earth's magnetic field at the time. Now, the Earth's magnetic field has changed polarity at irregular intervals in the past, so now a compass points to the North Pole. If you could go back to the last interval when the magnetic field was in the opposite direction, if you held a compass, it would point at the South Pole. With a marine magnetometer, we can map out stripes of ocean floor, and when we look at these stripes on a map, you can read that like a magnetic barcode that tells you the age of the different parts of the ocean floor and the rate at which it was formed.
Samples of rock from the sub-oceanic parts of the islands were also collected from the seabed using a dredge bag. These rocks were carefully sorted for later geochemical analysis. The tests would enable the geologists to determine the depth and temperature at which molten rock formed, and to estimate the chemical composition of the strata beneath the islands. Scientists hope that this data will improve our understanding of how the hot fluids released by the subducting plate cause the mantle to melt and form new volcanoes.
We're looking at the fundamental processes by which primitive, unevolved oceanic crust is transformed into what is a much more complicated system known as continental crust. Over time, continental crust changes, and over geological time, the last 4,500 million years, continental crust has been created at convergent plate margins such as the South Sandwich Islands. And bear in mind that continental crust is the prime source of practically all the metalliferous resources that we use in the world today.
As Endurance came to the end of the 17 days allocated to the deployment of field parties, a team of scientists led by John Smiley made ready for an extended survey of Candlemas Island. The party planned to establish a camp on the island for 4 weeks of intensive study and data gathering before being collected by landing craft from the James Clark Ross.
Working from a static camp, you can spend long periods of time looking at rocks in great detail, and that's what we did. We planned to spend the last 4 weeks camping on this island there. We also anticipated that although 4 weeks was more time than we actually needed to cover all the ground, we expected bad weather for part of this period, and that transpired. We lost 65% of our time because of bad weather, but there was still plenty of time remaining to actually cover the ground. So we have very, very detailed information for that island.
Candlemas is the most geologically varied of the islands, with a southern 550-metre-high landmass connected to a more recently formed island by a muddy sand flat. Past observations of the island indicate that one of the northern lava flows may have erupted in 1953, but the conditions found by the field party gave no indication of any likely volcanic activity during their stay, an essential consideration when assistance from Endurance would no longer be available. The greater part of John Smiley's work on Candlemas would involve surveying and mapping the island. His observations of the history of volcanic activity, recorded in successive layers of lava, had already begun to suggest a previously unsuspected aspect of the island's formation.
What we discovered was that each of the volcanoes formed simply by passive lava effusion. Magma simply welled up to the surface and overspilled and flowed down slope. And this happened time and time and time again. The evidence on the islands for highly explosive eruptions is trivial.
Because the islands have formed in an area where previously there was only oceanic crust, the chemical composition of the lava is of particular importance. Samples of rock collected from the islands can't have been contaminated by the older continental crust.
The system is remarkably simple. We understand the main tectonic elements. We have an oceanic trench 8 kilometers deep where South American oceanic crust is being consumed. We have the Scotia Sea plate oceanic crust on which the volcanoes are founded. We are very distant from any influence from pre-existing continental crust. So in that sense, we've stripped out a major reservoir which could affect the composition of magmas coming in. It makes it much simpler to interpret what we have.
Because the islands sit adjacent to the point of subduction, they are subject to regular earthquakes. As one plate moves beneath the other, tremendous pent-up forces are periodically released. Any earthquakes which occurred during the survey would be recorded by the ocean bottom seismometers. But in order to pinpoint the location and depth of these earthquakes, geophysicist Ed King set up a seismograph station on Candlemas.
They're like big microphones, really. They're a magnet moving in a coil in the same way that a microphone does. And they're set in motion when the ground moves, produces an electrical signal, and the equipment that we set up finally records that signal and puts it onto a form that computers can read, and we can store for later analysis.
The seismometers would record for the whole of the field party's stay on Candlemas. During the project, more than a dozen earthquakes were detected. The seismic energy recorded from these earthquakes helped to establish a clearer picture of what is going on deep beneath the surface at the point of subduction. It also contributed to the data collected by the James Clerk Ross to reveal information about the layers of rock through which the energy is travelling. Working in the field is a familiar experience for scientists with the British Antarctic Survey, and to many a welcome contrast to the months of data analysis which follow. At the end of a day, the scientists on Candlemas relaxed as best they could in their tents, but on board the James Clerk Ross, work continued around the clock. Time was running out, and the seismic survey was almost complete. Soon the ocean bottom seismometers would begin to surface, and if the vital data they'd recorded was not to be lost, the ship would have to return to the point of deployment to retrieve them. For the scientific team, the pressure was on.
We were working with very tight time constraints, so we really had to push on and just accept that some bits of our data set may be a little bit degraded. The fact that we were using ocean bottom seismometers which have timed releases put very tight constraints on our work and meant we had to try and predict very precisely how long it would take us to do the work which we wanted to do while the ocean bottom seismometers were on the seafloor.
In the end, all but one of the ocean bottom seismometers were recovered. The missing one simply failed to surface due to some unknown defect. With the ocean floor 6 kilometers down, there was no hope of recovering it. Back on Candlemas, terrestrial biologist Pete Convey was using the time to conduct research into the island's only vegetation, fragile moss growing on the hot volcanic ash. These primitive plants are the first stages of terrestrial life establishing itself on the islands and are probably the result of airborne spores coming from South America. Pete's research was concerned with investigating the ability of the various species of moss to tolerate the high soil temperatures generated by the volcano.
There we go.
At night, the lower temperatures at the very edge of the area I'm measuring would go down to around about 0. I mean, there's probably no ground heat influence there. The vegetation temperature near the vent will probably stay between 20 and 35, 24 hours a day. The mosses that you get around these vents are exceptional for the Antarctic. They only occur around these vents. And I hope to get some clues as to what their physiological tolerances are, such that you could say below a given temperature or below a given level of hydration, they won't be able to colonize.
As the 4 weeks drew to a close, John Smiley packed up the dozens of rock samples collected during his survey. Analysis of these fragments of lava would provide the clearest picture yet of the geological history of the island. Pete Convey's collection of moss required more careful preparation if they were to survive the long journey back to the laboratory in Cambridge, and a makeshift battery-powered dryer was used to preserve the moss for later classification. After 2 months of arduous work, the samples and data collected became the scientists' most precious cargo. One final trial awaited the field party on Candlemas. Bad weather had prevented the first attempt by the James Clark Ross to collect them from the island. In a brief break in the weather, a second uplift was attempted. Once again, the ocean swell, combined with the boulder-strewn beach, prevented the tender from landing. Eventually, the only solution was to fire a rocket ashore and to use a rubber dinghy to haul scientists and equipment off the island. In these hazardous conditions, the tents and much of their equipment had to be abandoned. At the conclusion of the 2-month project, the SLICE team headed back to Cambridge. The team had achieved almost all their objectives, but the results of their labours would now demand months of careful analysis. In many respects, the work had just begun.